It is believed that the two-layer shell of revolution is formed by cross-winding of the composite tape on a technological mounting made of mild steel. A kinematic model of deformation based on the non-classical theory of shells is used to describe geometric and physico-mechanical characteristics of the shell. For this, the components of the displacement vector are approximated by finite series of the orthonormal Lagrange polynomials. The construction of geometric dependencies is based on the relations of the simplest quadratic version of the nonlinear theory of elasticity. The stress and strain tensors in the composite layer are related by Hooke's law for an orthotropic body, with account for the degradation of the stiffness characteristics of the multilayer package due to the local failure of some elementary layers of the composite. Physical relations in the metal layer are formulated in the framework of the differential theory of plasticity. The model of degradation of stiffness characteristics of a multilayer package is formulated on the basis of the Hoffman criterion for the binder and the maximum stress criterion for the fibers calculated along the orthotropy axis of the layer. In addition, the strain rate dependence of strength characteristics of composite materials is taken into account. In particular, the unidirectional fiberglass, the strain characteristics of a material can be described by the regression function. An energy-consistent resolving system of dynamic equations for metal plastic shells of revolution and the natural dynamic boundary conditions are derived by minimizing the total energy functional of a shell as a three-dimensional body. By supplementing the obtained relations with the necessary number of initial conditions, we obtain a closed system of equations to analyze unsteady processes of deformation and strength of composite cylindrical shells loaded with an internal pressure pulse in a non-classical formulation. The numerical method for solving the formulated initial boundary value problem is based on an explicit variational difference scheme. The reliability of the proposed methodology for analyzing the ultimate deformability and strength of metal plastic cylindrical shells was assessed by analyzing the problem of dynamic deformation loaded with a pressure pulse imitating an explosion of a spherical explosive charge in the center of the shell, which was specified using the empirical dependence. We consider two-layer cylindrical shells with an inner steel layer of H1 thick and an outer fiberglass macro layer of H2 thick. Geometric and reinforcement parameters are presented. Physico-mechanical characteristics of a shell based on a unidirectional fiberglass. Material parameters of physical relations for a steel shell. The table presents the results of the comparative numerical experimental analysis of the two-layer metal plastic cylindrical shells, both with account for the strain rate dependence of their strain characteristics and at constant characteristics. It is evident from the table that the results of numerical analysis using the model accounting for the strain rate dependence of strain characteristics are in better agreement with the experimental data than the numerical results obtained using the model with constant strength characteristics. The table presents the results of the strain rate effect on the damage pattern of shells with different reinforcement schemes. It is evident from the table that the strain rate dependence of the strain characteristics, when accounted for, qualitatively changes the damage pattern of cylindrical shells, and the shells with an annular reinforcement structure have the least load-bearing capacity. The proposed computational model makes it possible to analyze the progressive damage of dynamically loaded shells of revolution, both taking into account the strain rate dependence of their strain characteristics, dynamic model, and at constant characteristics, static model. A comparative analysis of the numerical calculations of dynamic and static models with experimental data has been carried out, which shows that the calculation results for dynamic model are in better agreement with experimental data. For different shell reinforcement structures, qualitative differences in the character and size of failure zones were found, which were calculated using both dynamic and static models.